Stock market forecasting using time series analysis. Market. The stock market is a market that enables the seamless exchange of buying and selling of company stocks. Every stock exchange has its own stock index value. The index is the average value that is calculated by combining several stocks. This helps in representing the entire stock market and predicting the market's movement over time. The stock market can have a huge impact on people and the country's economy as a whole. Therefore, predicting the stock trends in an efficient manner can minimize the risk of loss and maximize profit. Here in this notebook, we will forecast the stock price of Arch Capital Group using ARIMA model. ARIMA. Autoregressive Integrated Moving Average, ARIMA, model converts non-stationary data to stationary data before working on it. It is one of the most popular models to predict linear time series data. ARIMA model has been used extensively in the field of finance and economics as it is known to be robust, efficient, and has a strong potential for short-term share market prediction. Load all the required libraries. Put the ARIMA package in your Python environment using the pip package manager. ARIMA is a popular library for time series analysis and forecasting in Python. It provides an easy-to-use interface for working with ARIMA, autoregressive integrated moving average, models, and other statistical models for time series data. The library also includes additional tools for model selection, diagnostics, and visualization. By running, you are installing the package so that you can import and use it in your Python scripts or notebooks for time series analysis tasks. The exclamation point at the beginning of the command indicates that it should be executed as a shell command instead of a regular Python statement. In environments like Jupyter Notebook or Google Colab, this allows you to run shell commands directly within the notebook cells. Is a Python script that imports necessary libraries and modules for time series forecasting, sets some configurations, and prints the file paths of input files. 1. Import necessary libraries and modules. OS. The OS module in Python provides functions for interacting with the operating system. Warnings. The Warnings module provides a way to issue warning messages to the user. NumPy, a library for the Python programming language, adding support for large, multidimensional arrays and matrices, along with a large collection of high-level mathematical functions to operate on these arrays. Pandas, a library for data manipulation and analysis. In particular, it offers data structures and operations for manipulating numerical tables and time series. Matplotlib.pyplot, a plotting library used for 2D graphics in Python programming language. Pylab.rcprams, a module for managing default settings of the Matplotlib library. Stats models, a Python module that provides classes and functions for the estimation of many different statistical models, as well as for conducting statistical tests and statistical data exploration. ARIMA, a library for time series forecasting with the ARIMA model. 2. Configure warnings and plotting style. Warnings.filter warnings, ignore all warnings. plt.style.use, 538, use 538 style for the plots. rcprams, figure.figsize, equals 10, 6, set the default figure size to 10 inches in width and 6 inches in height. 3. Loop through the input files and print their paths. For dirname, file names in os.walk/kaggle/input, loop through the directory /kaggle/input and its subdirectories. For file name and file names, for each file found in the directory. Print os.path.join, dirname, file name, print the full path of the file. This code reads a CSV file containing stock price and volume data and converts it into a pandas data frame. The CSV file is located at /input/price-volume data for all stocks at /stocks/acl.us.txt. Here's a step-by-step explanation. 1. Date parse equals lambda dates, pd datetime.striptime, dates, %y-%m-%d. This line of code defines a lambda function called dateParse, which takes a date string as input and converts it into a datetime object using the format %y-%m-%d, i.e., year, month, day. 2. PD read_CSV, /input/price-volume data for all stocks at /stocks/acl.us.txt, set equals, index_call equals date, parse_date sadface date, date_parser equals dateParse. This line of code reads the CSV file using the pandas read_CSV function. The function takes several arguments. The file path of the CSV file. Sep equals indicates that the values are separated by commas. Index_call equals date sets the date column as the index for the data frame. Parse_date sadface date specifies that the date column should be parsed as datetime objects. Date_parser equals dateParse uses the previously defined dateParse function to parse the date strings in the date column. 3.filna 0. This method is called on the resulting data frame to replace any missing or NaN values with 0. The result is a pandas data frame containing the stock data with the date column as the index, and any missing or NaN values replaced with 0. The code is a variable name that likely refers to data related to stocks, such as stock prices, volume, or other financial information. This variable might hold information in a data structure like a list, dictionary, or a pandas data frame, depending on how it was defined in the code. However, without more context or additional code, it is impossible to provide a more specific explanation of what this code does. Per day closing price of the stock. Line chart of the closing prices of Arch Capital Group stock over time. 1. PLT.figure, figSi sat face 10, 6. Create a new figure with the specified width, 10, and height, 6. 2. PLT.grid, true, add a grid to the plot for better readability. 3. PLT.label, date, set the label for the x-axis as date. 4. PLT.label, close prices, set the label for the y-axis as close prices. 5. PLT.plot, stock_data, close, plot the close column of the stock_data data frame on the line chart. This column contains the closing prices of the stock. 6. PLT.title, Arch Capital Group closing price, set the title of the plot as Arch Capital Group closing price. 7. PLT.show, display the plot as the data in our series through a probability distribution too. Snippet creates a plot, graph, that represents the distribution of the data in the df_close data frame using a kernel density estimation, KDE, plot. df_close is assumed to be a pandas data frame containing data you want to visualize. Plot is a function provided by pandas to create various types of plots using data from a data frame. Kind equals KDE specifies that the type of plot to be created is a KDE plot. KDE is a non-parametric way to estimate the probability density function of a random variable. It essentially shows the shape of the distribution, allowing you to see where data points are more concentrated. Also, a given time series is thought to consist of 3 systematic components, including level, trend, seasonality, and one non-systematic component called noise. These components are defined as follows. 1. Level, the average value in the series. 2. Trend, the increasing or decreasing value in the series. 3. Seasonality, the repeating short-term cycle in the series. 4. Noise, the random variation in the series. First, we need to check if a series is stationary or not because time series analysis only works with stationary data. ADF, Augmented Dickey-Fuller, test. The Dickey-Fuller test is one of the most popular statistical tests. It can be used to determine the presence of unit root in the series, and hence help us understand if the series is stationary or not. The null and alternate hypothesis of this test is: null hypothesis, the series has a unit root, value of a equals 1. Alternate hypothesis, the series has no unit root. If we fail to reject the null hypothesis, we can say that the series is non-stationary. This means that the series can be linear or different stationary. If both mean and standard deviation are flat lines, constant mean and constant variance, the series becomes stationary. So let's check for stationarity. Defines a function called test_stationarity that takes a time series dataset as input and tests its stationarity. Stationarity is an important property of a time series that indicates whether its statistical properties, such as mean and variance, remain constant over time. Many time series models assume stationarity, so testing for it is often a necessary step in time series analysis. The function performs the following steps. 1. Calculate the rolling mean and rolling standard deviation of the input time series using a window size of 12. The rolling mean is essentially a moving average, while the rolling standard deviation measures the variability of the data within the rolling window. 2. Plot the original time series, rolling mean, and rolling standard deviation in a line chart using Matplotlib. The original time series is plotted in blue, the rolling mean in red, and the rolling standard deviation in black. A legend and title are added to the plot for better understanding. 3. Perform the Dickey-Fuller test on the input time series using the Fuller function from the stats models library. This test is a statistical test for stationarity, with the null hypothesis being that the time series is non-stationary. A small p-value, typically smaller than 0.05, indicates that we can reject the null hypothesis and consider the time series to be stationary. 4. Print the results of the Dickey-Fuller test, including the test statistic, p-value, number of lags used, and the number of observations used. Additionally, print the critical values for different significance levels. 5. Finally, the function is called with the input df_close, presumably representing a data frame containing the closing prices of some financial asset. In summary, this code helps visualize and test the stationarity of a given time series, which is an essential step in many time series analyses and forecasting tasks. Through the above graph, we can see the increasing mean and standard deviation, and hence our series is not stationary. We see that the p-value is greater than 0.05, so we cannot reject the null hypothesis. Also, the test statistics is greater than the critical values. So the data is non-stationary. In order to perform a time series analysis, we may need to separate seasonality and trend from our series. The resultant series will become stationary through this process. So let us separate trend and seasonality from the time series. Composes a time series into its trend, seasonality, and residual components using the seasonal_decompose function from the stats models library in Python. The input time series is df_close, and the decomposition model is set to multiplicative. The frequency of the seasonality component is set to 30. After decomposing the time series, the code creates a new figure using plt.figure. Then, it plots the decomposition results using result.plot. Finally, the size of the resulting figure is set to 16 inches in width and 9 inches in height using figure set_size_inches, 16, 9. The output of this code will be a plot that shows the original time series, the trend component, the seasonal component, and the residuals in separate subplots. This visualization can help in understanding the underlying patterns and characteristics of the time series data. Log of the series to reduce the magnitude of the values and reduce the rising trend in the series. Then after getting the log of the series, we find the rolling average of the series. A rolling average is calculated by taking input for the past 12 months and giving a mean consumption value at every point further ahead in series. This code is used to analyze and visualize the trend and standard deviation of a time series data, typically stock market closing prices, to determine if it is stationary or not. If the data is not stationary, it eliminates the trend to make it stationary. 1. Import the necessary libraries. It imports the required RCparams from the PyLab library for setting the figure size and the NUPI library as NP. 2. Set the figure size, RCparams, figure.figsize equals 10, 6 sets the width and height of the plot to be 10 inches and 6 inches, respectively. 3. Calculate the logarithm of the data, df_log equals np.log, df_close, calculates the natural logarithm of the time series data, closing prices, and stores it in the variable df_log. 4. Calculate the moving average and standard deviation, moving_average equals df_log.rolling, 12.mean, and std_div equals df_log.rolling, 12.std, calculate the rolling mean and standard deviation of the law transformed data using a window size of 12. 5. Set up the plot. The code sets up a plot with a legend and title. The legend is placed at the best location, and the title is set to moving average. 6. Plot the standard deviation and moving average, plt.plot, std_div, color equals black, label equals standard deviation, and plt.plot, moving_average, color equals red, label equals mean, plot the standard deviation in black and the moving average in red on the same plot. 7. Display the legend, plt.legend, displays the legend on the plot. 8. Show the plot, plt.show, renders and displays the plot on the screen. The resulting plot shows the moving average in red and the standard deviation in black, which helps to visualize the trend and volatility of the time series data. If the data is not stationary, the trend will be eliminated to make it stationary for further analysis. We are going to create an ARIMA model and will train it with the closing price of the stock on the trained data. So let us split the data into training and test set and visualize it. This code is used to split a given dataset into training and testing sets, and then visualize the data using a line plot. 1. The dataset is stored in a variable called df_log. 2. The code splits the dataset into two parts, train_data and test_data. The training data contains 90% of the dataset, while the testing data contains the remaining 10%. This split is performed by slicing the data frame based on the length of the dataset. 3. A new plot is created with a figure size of 10 by 6 inches. 4. Grid lines are added to the plot for better visualization. 5. X and Y axis labels are set to dates and closing prices, respectively. 6. The entire dataset, df_log, is plotted in green color, representing the trained data. 7. The test_data is then plotted in blue color, representing the test data. 8. A legend is added to the plot to distinguish between the train and test data. In summary, this code splits the input dataset into training and testing sets, and then creates a line plot to visualize the closing prices of the dataset with respect to dates. The green line represents the training data, and the blue line represents the testing data. to choose parameters P, Q, D for ARIMA model. Last time we chose the value of P, D, and Q by observing the plots of ACF and PACF, but now we are going to use auto ARIMA to get the best parameters without even plotting ACF and PACF graphs. ARIMA automatically discovered the optimal order for an ARIMA model. The auto_ARIMA function seeks to identify the most optimal parameters for an ARIMA model and returns a fitted ARIMA model. This function is based on the commonly used AR function, forecast auto.arima. The ARIMA function works by conducting differencing tests, i.e., Kwiatkowski, Phillips, Schmidt, Shin, augmented Dickey-Fuller, or Phillips, Perron, to determine the order of differencing, D, and then fitting models within ranges of defined start_P, max_P, start_Q, max_Q ranges. If the seasonal optional is enabled, auto_ARIMA also seeks to identify the optimal P and Q hyperparameters after conducting the Canova-Hansen to determine the optimal order of seasonal differencing, D. This code is using the auto_ARIMA function from the PyTorch library to automatically find the best ARIMA model for a given time series dataset called train_data. ARIMA stands for Autoregressive Integrated Moving Average, a popular forecasting method for univariate time series data. Here's a breakdown of the code. 1. Model_AutoArima equals auto_ARIMA, train_data. The auto_ARIMA function is called with train_data and several parameters to automatically find the best ARIMA model. The resulting model is stored in the variable model_AutoArima. 2. Start_P equals 0, start_Q equals 0. The initial values for the P, autoregressive order, and Q, moving average order, parameters are set to 0. 3. Test equals ADF. The augmented Dickey-Fuller test is used to find the optimal value for the D parameter, which represents the order of differencing needed to make the time series stationary. 4. Max_P equals 3, max_Q equals 3. The maximum values for the P and Q parameters are set to 3. 5. M equals 1. The frequency of the time series is set to 1, indicating no seasonality. 6. D equals none. The initial value for the D parameter is set to none, so the model will determine the best value for D. 7. Seasonal equals false. The model does not consider seasonality in the time series. 8. Start_P equals 0, D equals 0. The seasonal components of the ARIMA model are not used, as seasonal is set to false. 9. Trace equals true. The trace parameter is set to true, which means the function will print the evaluation results for each tested model. 10. Error_action equals ignore. Suppress_warnings equals true. Errors and warnings are ignored during the model search process. 11. Stepwise equals true. The stepwise algorithm is used to search for the optimal ARIMA model, which is a more efficient approach than an exhaustive search. 12. Print model_AutoArima.summary. The summary of the best ARIMA model found is printed. 13. Model_AutoArima.plot_diagnostics. Fig's-eye sadface 15. 8. Diagnostic plots of the residuals are generated to evaluate the model's performance. 14. plt.show. The diagnostic plots are displayed using the show function from the matplotlib.pyplot library, which is assumed to be imported as plt. Interpret the plot diagnostics. Top left, the residual errors seem to fluctuate around a mean of 0 and have a uniform variance. Top right, the density plot suggests normal distribution with mean 0. Bottom left, all the dots should fall perfectly in line with the red line. Any significant deviations would imply the distribution is skewed. Bottom right, the correlogram, aka ACF plot, shows the residual errors are not autocorrelated. Any autocorrelation would imply that there is some pattern in the residual errors which are not explained in the model. So you will need to look for more X's, predictors, to the model. Overall, it seems to be a good fit. Let's start forecasting the stock prices. Next, create an ARIMA model with provided optimal parameters P, D, and Q. ARIMA model provided the value of P, D, and Q as 1, 1, and 2 respectively. Building a time series forecasting model using the ARIMA, Autoregressive Integrated Moving Average, method. ARIMA is a popular method for time series modeling because it can handle data with trends and seasonality. Here's a step-by-step explanation of what this code does. 1. It first defines a model using the ARIMA function from the stats models library. This function takes two main arguments, the training data, train_data, and the order of the ARIMA model, order sadface 1, 1, 2. The order is a tuple of 3 values, representing the following components. P, 1 the number of autoregressive terms, AR component. D, 1 the degree of differencing, I component. Q, 2 the number of lagged forecast errors in the prediction equation, MA component. 2. Next, it fits the model to the training data using the fit method with the option DISP equals -1. The DISP parameter controls the frequency of the output during the iterations. In this case, DISP equals -1 indicates no output. 3. Finally, it prints the summary of the fitted model using the summary method. This will show various statistics and diagnostics related to the model, including the coefficients of the ARIMA model, the standard errors, the p-values, and other information that helps in evaluating the performance and validity of the model. Start forecast the stock prices on the test dataset, keeping 95% confidence level. This code generates a forecast using the fitted model for 321 future data points with a 95% confidence interval. 1. Fitted.forecast 321 alpha equals 0.05 is a method called that forecasts the future values of the time series using the fitted model. The method takes two arguments. 321 is the number of future data points to forecast. Alpha equals 0.05 specifies the level of uncertainty, which is 5% in this case. This means that the confidence interval will be 95%, 1 alpha equals 0.95. 2. The forecast method returns three values. FC, this is the forecasted values for the next 321 data points. SE, this is the standard error associated with each forecasted value, which can be used to measure the uncertainty of the forecast. CONF, this is the 95% confidence interval for each forecasted value, which provides an interval of possible values for each data point with 95% confidence. Results. To visualize the actual and predicted stock prices of the Arch Capital Group using the Python library matplotlib. The code does the following. 1. Convert the forecasted stock prices, FC, lower confidence interval, CONF, 0, and upper confidence interval, CONF, 1, into pandas series with the same index as the test data. This is done using PD series function. 2. Create a new figure with a specified size, 10 by 5 inches, and resolution, 100 dpi, using plt.figure function. 3. Plot the training data, train_data, on the figure using plt.plot function, with a labeled training data. 4. Plot the actual stock prices, test_data, on the figure using plt.plot function, with a blue color and a labeled actual stock price. 5. Plot the predicted stock prices, FC_series, on the figure using plt.plot function, with an orange color and a labeled predicted stock price. 6. Fill the area between the lower and upper confidence intervals, lower_series and upper_series, using plt.fill_between function, with a black color and 10% opacity, alpha equals 0.1. 7. Set the title of the plot as Arch Capital Group stock price prediction using plt.title function. 8. Set the x-axis label as time and y-axis label as Arch Capital Group stock price using plt.label and plt.alabel functions respectively. 9. Add a legend to the upper left corner of the plot with a font size of 8 using plt.legend function. 10. Display the plot using plt.show function. In summary, this code creates a plot to visualize the actual and predicted stock prices of Arch Capital Group along with the confidence intervals using the training and test data provided. You can see our model did quite handsomely. Let us also check the commonly used accuracy metrics to judge forecast results. Calculates and prints the performance metrics of a forecasting model by comparing its forecasts, FC, with the actual values from the test data, test_data. 1. Mean squared error, MSE. It calculates the average squared difference between the predicted values, FC, and the actual values, test_data. A lower MSE value indicates a better fit of the model. MSE equals mean_squared_error, test_data, FC. Print, MSE, plus str, MSE. 2. Mean absolute error, MAE. It calculates the average absolute difference between the predicted values, FC, and the actual values, test_data. A lower MAE value indicates a better fit of the model. MAE equals mean_absolute_error, test_data, FC. Print, MAE, plus str, MAE. 3. Root mean squared error, RMSE. It calculates the square root of the MSE. This metric is useful because it has the same unit as the original data. A lower RMSE value indicates a better fit of the model. Reams equals math.sqrt, mean_squared_error, test_data, FC. Print, RMSE, plus str, reams. 4. Mean absolute percentage error, MAPE. It calculates the average percentage error between the predicted values, FC, and the actual values, test_data. This metric is useful for comparing the performance of different models on the same dataset. A lower MAPE value indicates a better fit of the model. MAPE equals np.mean, np.abs, fc test_data, /np.abs, test_data. print mate plus str mate. In summary, this code calculates and prints the performance metrics MSE, MAE, RMSE, and MAPE of a forecasting model by comparing its forecasts with the actual values from the test data. These metrics help to evaluate the accuracy and fit of the model.